Okay, for our third lesson in our final unit, we're going to focus on what are called tangent lines. You've probably heard that word before as we explored kind of some basic trigonometry, just dealing with the old SOHCAHTOA shortcuts of sine, cosine, and tangent ratios, writing those to find the lengths of lengths of the sides given the measure of an angle in one of the sides of a triangle, or finding the measure of an angle given two side lengths. But we're going to focus on tangent lines today. These are lines that barely touch the circle, and as they intersect it in exactly one point, we're going to find out that there's some special relationships formed with the angles that are formed there. And so we're going to have a little exploration here. The first is to note that a tangent is simply a line that's in the same plane as a circle. Okay, so some geometric verbiage there. But it touches the circle in exactly one point. It touches just at point B. It doesn't touch the circle to the left of point B. It doesn't touch it to the right of point B. It touches it at exactly one point. All right? We say that BA is a tangent ray. BA is a tangent segment. BA with a double arrow would be a tangent line. And the point B, where it touches, is referred to as the point of tangency. So there's a little bit of vocabulary there, verbiage there. We're going to try our best to focus on using the correct words and notations. We're going to deal with rays and segments and lines. But the big thing here is to recognize what's happening that's extra special here at point B, as this line barely touches this circle, all right, as it is just tangent to the circle. Well, if a line is tangent to a circle, then that line is perpendicular to the radius at that point of tangency, okay? So what we have here is that this tangent line is tangent to circle O at point P, meaning that the angles formed at point P with the radius are going to be right angles, all right? That's going to be useful stuff to us. We know that whenever right angles are involved, that we have some awesomeness that we can do, whether that's the trigonometry, obviously we're using a tangent line here, or if we get to use Pythagorean theorem or other explorations there within right triangles. So here is such a situation where line segments ML and MN are tangent to circle O at points L and N, which means that these angles that are formed with the radius ON and OL are going to be right angles. These are right angles here. And so the question is, how do I find the measure of this angle out here at point M? Well, essentially what we're going to do is we can have two approaches here. The number one approach is to say, hey, this is a quadrilateral, therefore the sum of the measures of the interior angles is 360 degrees. All right? And so we take 360 minus these two 90s, minus this 117, and that would tell us the measure of the angle at point M. Another way to do that is to recognize that if these are both 90, then that means that these angles, because these make 180, that means that these angles would have to be supplementary to each other. Those angles would have to be supplementary to each other. So we can simply take 180 and subtract 117 to find that the measure of the angle at M, or the value of x in this case, is 63. All right? The measure of angle M would be 63 degrees. Again, two ways we can do that. 117 plus x equals 180. Or you can start it kind of a step before, which says that 90 and 90 and 117 and x makes 360. Well, when you subtract off this 180, you're left with 117 plus x equals 180. Do a little bit more subtraction, find out the value of x. Here's another situation in which segment ED is tangent to circle O at point D, obviously, which means that there's a right angle in this triangle. There's a right angle. This angle is 38 degrees. And so we can do a little triangle angle sum theorem to find out the measure of the angle at E. All right? And so what we're going to find out here is that we would have 90 and 38 is equal to x. Another way to do that is to recognize that, plus x equals 180 would be our equation. Another way to understand that would be to recognize that these angles are complementary, meaning that the sum of 38 and x is equal to 90 degrees. All right? So 90 plus 38 plus x makes a triangle 180 degrees. When we subtract out 90, we recognize that, hey, these two angles, the 38 and the x, are going to have to add up to 90, which makes then our math pretty straightforward to find the value of x. The measure for angle E would be 52 degrees. The value of x would just be 52. Again, we can either create the equation using triangle angle sum, or we can use it using, or write it using complementary angles. All right? So supplementary angles with the quadrilateral, complementary angles with the right triangle. And then here would be an application of using the angles formed with those tangent lines. So here we have kind of like a pulley system, all right? And so in this situation, we've kind of got two pulleys. We've got a belt that goes around. And the way that these fit together is such that the pulley is going to be at that point where it starts to then wrap around the circle, is going to be the point of tangency, all right? And so here we have radii drawn. The radius here is 8 inches. The radius of this larger is 14 inches. Our job is to figure out what is the distance between these centers of these pulleys. And so it's kind of a strange situation to see how this might work together. But what we're going to do to shortcut this work, to make it a little more manageable for us, is instead of dealing with this quadrilateral, we're going to make a rectangle and a triangle. All right, we're going to make a rectangle and a triangle. Now here is an issue with this that you may encounter. A foreseeable situation. All right, and that issue that you may encounter is that you may think that there is a right angle here. All right, this radius and that segment are not necessarily perpendicular. In fact, they shouldn't be perpendicular. They better not be. If I drew a segment such that I made a rectangle here, then we know that this distance is 35. We know that if this is 8, then this distance is 8. Meaning that the remaining portion of the 14 inches, if this is 8 inches and this whole thing's 14, then 14 minus 8 is going to give us 6. So this is going to be 6 inches here. Now the question is, how do I use the 6 and the 35 to figure out the length of this other side of the triangle? You heard me mention earlier that we are going to use Pythagorean theorem, but here's the issue that I'm alluding to, that I mentioned moments ago. And that is we want to put a right angle down here. This is not where our right angle goes. If you notice that when you drew your rectangle, you have a right angle here, well, that means that you have a right angle there. Perpendicular segments make all right angles. All right? So that means our right angle is here. Our right triangle is like so, with 6, 35, and then the distance that we're finding between. The way the triangle is drawn, however, we may get confused and say that the hypotenuse is 35, and that this leg is 6, and then we're trying to find the length of a leg. All right, so the question is, which approach do we want to take? Well, we want to do it, first of all, correctly. We want to do it in a way that makes sense. We drew a rectangle here so that we could have a right triangle there. The right angle, however, is up here. All right, here's the right angle. And so it is not perpendicular down here, it is perpendicular up there. That will be an issue with the way that we draw things. Even the way I drew this, it's like, oh, I could draw that right there, and you'd think, oh, that's a right angle. I can't have two right angles in a triangle, though. So this one has to be a right angle, this one is not. So we get a little Pythagorean theorem. These are the legs, and this is the hypotenuse that we're actually finding. So we have an easier situation than having to do some massive solving. We don't have to do subtraction and then square rooting. All we have to do is add and then square root. All right, so it's a little bit more manageable. And so I'm going to use my calculator, not for this part. I know 6 squared because I took that class already. But 35, I forgot that one. That's 1225, and that gives us x squared. What we're going to find out here is that we're going to get a sum total here, and it might sometimes get a little bit messy. And if it ever gets messy, that's going to be okay. This is going to be the first time this year, where we get to approximate the value of x. So we're going to say x is approximately equal to 35.5 inches. All right, 35.5 inches. We're not going to simplify that radical. You're welcome. But we are going to do Pythagorean theorem. And then we're going to actually type the square root of 1261 in our calculators and get an approximated value in inches. Okay, so that again, we make a rectangle, draw the right angles, work from there. The very last part that we're going to discuss, watch that example again if you need to, pause the video, rewind it so you can go back and see that example again if you need to. If a line is perpendicular to the radius at its endpoint, then that line is tangent to the circle. It's basically the converse of that first theorem that we had. All right? If the line is tangent, then it's perpendicular to the radius. If the line is perpendicular to the radius, then it's tangent to the circle. All right? So it's just kind of thinking about this in reverse. All the same concept, just thinking about it now just thinking about it backwards. Same idea, just think about it in reverse. And now this one right here, example 3, note that I'm going to trick you. I'm gonna trick you here, and that's intentional. It's intentional to trick you, but I'm telling you that I'm tricking you, so it doesn't count as tricking you. But here we're gonna have a situation where we have circle O, and we have that PO is, point P is outside of circle O. There's circle O. Here's point P, and it's outside of the circle such that PO is 12. That's from here all the way to the center, all right? PA is 13, and the radius is 5, all right? So here's the question. Is this a right angle? All right, what kind of angle is this? Is this going to be a right angle? Yes or no? All right, so intentionally I drew this to make it look like this was a right angle, all right? And so this is what I'm talking about, how I'm trying to trick you, all right? Because our brain wants to make that, happen. It wants it to be a right angle. And we know that if we were to take 5 squared and 12 squared, we would get 13 squared. So this is why this is a little bit tricky to us. Because if I take 5 squared and 12 squared, I am going to get 13 squared. That works. 25 and 144 makes 169. It checks out. But look at the way that this is written versus the way that this picture is drawn. Okay, what you should notice is that these would have to be the legs of the triangle, and this would have to be the hypotenuse. The hypotenuse cannot be longer than one of the legs, and we would have to have 5 squared and 13 squared equal 12 squared, but they don't. All right? So, given this situation, the picture would, in reality, have a right angle here, and then point, what is this? This is PO, this is PA. And then we would notice that this can't be tangent to the circle because I can't have 2 right angles in my triangle, right? These would be perpendicular. 5 squared and 12 squared would make 13 squared, but we can't have 13 squared and 5 squared equal 12 squared. So then this triangle that exists, in reality here is not going to be a right triangle with the right angle on the circle, all right? Watch that again if you need to, kind of go back. That can be a little bit confusing because I'm intentionally trying to trick you here into thinking that this is going to be a right triangle with the right angle at point A, but it's a right triangle with the right angle at the center. And that's not helpful to us because that means that this, well, I mean, it's helpful, but it means that this PA is not tangent. To circle O. Kind of hard to write circle O. All right, moving on though. Let's apply that, and then this one's not going to be as tricky. It's the same example. We're just working this a little bit in reverse, and we're going to say, well, is this segment tangent to this circle at N? The question is this a right angle? Yes or no? And so if we can show that 7 squared and 24 squared makes 25 squared, then yes, this is a right triangle. It's the converse of the Pythagorean theorem. If a squared and b squared add up to c squared, then yes, this triangle is a right triangle. So the question here is, does 7 squared and 24 squared make 25 squared? All right, that's really the question that we're asking. And we can confirm that right here that it actually works. 7 squared plus 24 squared is going to be 625. And that does, in fact, equal 25 squared. Yes. So this is a right triangle with these the legs, that the hypotenuse. So if the legs are the sides that are perpendicular, then yes, ML is tangent to circle N. Put a dot in the middle of the circle there. Circle N. ML is tangent to circle N because ML is perpendicular to the radius at point L. All right. I think that there's one more. Oh, there's two more of these. We got a couple slides here. Again, pause the video as you need if those examples go too fast. The two segments tangent to a circle from a point outside the circle are congruent. All right, and this is actually not too difficult of a proof. We would know that these, if we know that, that they are tangent, then we know that these are right angles. We don't know their lengths yet, but we do know that the radii are congruent. We do know that this segment is congruent to itself, and so we have hypotenuse leg congruence. So these two triangles are congruent, therefore by CPCTC, BA and BC are congruent. If you want to write out that proof, that would be awesome. Like, that'd be awesome. Maybe extra credit. You want to write out the proof for why BA and BC are congruent to each other. But so if these are both tangent to the circle, then that means that this segment is congruent to that segment. All right? And the way that we apply that is when we have a circle inscribed in a triangle or maybe some other figure. And that might seem like kind of a stretch. We did a little bit of this with regular polygons, etc. And so this might be, a neat exploration, or it might be terrible. It's kind of up to you. But basically, what we're going to find out is that if the circle is inscribed in here, then that means it's making a right angle at the radius at these magical points that I've got identified here, x, y, and z. Okay? So, if this circle is inscribed in the triangle PQR, inscribed just means it's drawn in and it only touches barely at one point on each of the sides. It's kind of a neat concept. This year we skipped Unit 5, unless you transferred in from a different teacher's class and then maybe they covered it, but we covered radicals instead. That was our goal. So what we notice here is that these two segments are tangent segments originating from the same point, so that means that these will be congruent to each other. These two segments are tangent lines, or line segments, originating from the same point, so they will be congruent. And finally, these two are tangent line segments emitting from the same point, so these will be congruent to each other. All right? It does not mean that this segment is congruent to that segment. It means that these two are congruent. All right? These two are not congruent, these two are not congruent, these two are not congruent. It's from the same point. So these two are congruent, these two, and those two. Make a note of that if you want to, please. Actually, please make that note in your notes, saying that x is not the midpoint of PQ. Rather, PX and PZ are congruent. So this is 15 centimeters and 15 centimeters. This is 17, and this is also 17 centimeters. And so the question is, what is the length of QY is what we're trying to find. Segment QY's length, we're going to try to determine what that is. So how do we do that? Well, we're going to use perimeter. We know that perimeter is 88. And the perimeter is the lengths of all the sides added together. So what we have is 15 and let's call this x for one side. And then we have x and 17. And then we have another side, 17 and 15. All right? So we've got this side, 15 and x. We've got x and 17. We've got 17 and 15. All right? Or if you want to go faster, you can say 2 15s, 2 17s, and 2 x's. Right? So that's another way in which we can do that. I'll just do it this kind of the brute force way, adding all these pieces up. That's 30 and 34 makes 64. X and x make 2 x's. Subtracting the 64, we get 24 equals 2 x's. And so 12 is equal to x. The length of segment QY is 12. All right? Then we can double check that, making sure that we do a good job. Like I said, another way in which we could do that is say that 88 is 2 15s, 2 17s, and 2 x's. 2 17s and 15s and x's. All right? So let's divide both sides by 2. 44 is 17 and 15 and x. Let's subtract 17 and 15. 44 minus 17 and 15 gives us 12 is x. That's another way in which we can do it. So do the algebra or the arithmetic in whichever way you want, but we've got to create a perimeter equation. We've got to combine and solve. We're doing Algebra 1, Chapter 2. All right? All right. That's the end. All right, so as you have questions, what I'd love for you to do is write those in your notes. So have a spot in your notes right now where you say, my question is, or I'm confused about, and then we can talk about it in class. If there's no confusion, then we should be able to rock through our classwork without any hassle. All right, so if you've got questions, go ahead and put those in the notes.